So Han has a question regarding how do we do the steps of hypothesis test? I think that's really your question, right? And how to accomplish it in Excel, step by step, right? So we're going to look at 10.95. Again, maybe we went through it too fast last time. All right. So let me read. You both have access to 10.95, right?
Yes.
All right.
Yes.
Average and select for households in the sample, the average amount of life insurance is 245,800. A sample standard deviation of 25,500 using a non-directional hypothesis test, and a level of significance of choice. I believe we used what did we use? We used 2%, right? I decided 2%. What conclusion would be reached? All right. So let's take a look at the solution and then show you how to do it in Excel also. So here's the information that was given in the problem, top row here. Here's your hypothesis tests, right? Any questions about that so far? You good with that, Han? All right.
Yeah.
And then, of course, n is equal to 30, which is large enough to say that the sampling distribution is normal. You have a simple random sample that was performed, which is required for doing this test also. Sigma, the population standard deviation, is unknown, so we're going to do a t-score, not a z. All right, and the t-score formula is this here. It's the numerator is the sample mean minus the proposed population mean, which is the null population mean, divided by the standard error, which is the sample standard deviation divided by the square root of the sample size. You do the arithmetic, you come up to 2.109 as your t statistic or t-score. Now, what we do is we know this is a two-tailed test, so we're going to have not only the t that was calculated, which is positive, but we're going to have a negative of it on the left side. All right, just know that. And what we use to find this area here is, and this is just 1/2 the p-value, is we use t distribution. So let me just stop sharing here. I'll open up Excel. Oh, hold on 1 second. I'm going to get back to the main screen here. Okay. So I'll open up Excel. Just start with a blank worksheet. All right, here we go. All right, so let me share the worksheet with you. All right, so what we want is, what we have so far is that t, right? T statistic.
Right.
We could even calculate it right into the spreadsheet here. So I'm going to put t statistic. All right, I'm going to actually calculate it. So the numerator is simply the sample mean, 45,800, minus the null mean, which is 235,600, divided by standard error, and the population standard deviation is 25,500. That's divided by the square root. Oops. Of what? 30, right? 30. All right. And there's my 2.19089. All right, so that's my t statistic. And then I want to do a t distribution. So this equal t. Notice there's a t distribution. That's the one I want, t dot distribution. What I need to put in is the value, which is this number here, right? And then what else do I need? Degrees of freedom, that's 29, right? Sample size -1. And then cumulative, yes, we want cumulative, which is true, right? Close the parentheses. Now, what I just came up with is not the number I want. Because if you look at the, let's stop sharing for a minute. Go back to the solution. What I'm interested in is this area here, right? Area to the right. What I found was the area to the left. Remember, in the normal distribution and the t distribution, when it asks for cumulative area, it's asking for the left, cumulative area to the left.
Right.
I'm interested in the area to the right, which is 1/2 the p-value. Is this area plus that area is the p-value. Right? Is that correct?
Right.
Yeah.
Yes.
All right, so go back to Excel. I'll share the Excel screen again. All right, so I'm going to put right below here p-value. I know the p-value is going to be double the right tail, right? So the p-value is going to be 2, be equal to 2 times 1 minus the left area to the left. There's my p-value. Okay?
Mhm.
It's just basically 1 minus this number up here, 0.98, times 2.
Mm-hmm.
So that's my p-value, 0.037 if you want to round it to 3 decimal places. And then you compare it to my alpha. What's my alpha? 0.02. If the p-value is greater than alpha, I'm not going to reject the null hypothesis. In this case, my alpha is 0.02. It's 2%. This is bigger than 2%. Do not reject.
Okay. Gotcha.
Does that make sense?
Yes.
And I want you to go through these steps because that's the only way you'll learn it. If we simply did a t-test, right, and let the computer do everything, I could teach anybody to do that, right?
Mm-hmm.
They wouldn't have learned anything. So better go through all the steps. I mean, for example, I might ask you what the t statistic is, right, as part of the steps that you're taking, and there's no need, obviously if you did an actual t-test on the computer, it wouldn't give you that answer. It would just give you the final answer, the p-value probably. All right, and then, in this case, then you would say at the 2% significance level, there's not enough evidence to reject the claim that the average household has $235,600 in life insurance. Okay, there's not enough evidence because the p-value is bigger than alpha. All right. Are we good with that, Han? Are you good?
Yeah. If it's the z-score, what function shall we use? Because we are using t-score here. T-stat.
You would use normal. Equal n.
Or just use norm.
A normal distribution. Norm.dist. This one. Just type in NO and then it'll show you the list in Excel and just pick norm distribution. That's the one you want.
Okay. Okay.
Okay, I'll give you, again, I didn't do it yet, but I'll give you some
But in
homework.
the normal distribution, is there anywhere we can input the z-score? I saw it asked for x mean
Absolutely.
standard deviation.
Well, you put it just like we did with the t-score. You put it for the first number. The first number.
Oh, okay, okay, gotcha.
Where it says x, that's where you put it, right there, x.
Okay.
X. It's asked for
And
the
mean
mean.
is gonna be 1.
No, the mean is going to be 0, standard deviation 1, because it's a z-score.
0.
Yeah.
Okay, gotcha.
Yeah. Does that make sense? Now there might be a, let me see if there is
Sure.
a norm for z. I would, yeah, norm S must be standard normal. See norm S distribution here? That's probably for the standard normal. You could use that just for the standard normal, but I would just, you know, if you click that one, the only thing it's asking for is the Z and then true or false for cumulative. So if you want, you can use that one instead.
Okay, okay.
Just play around in Excel. Like I tell most of my students, you cannot damage anything by playing around. All right. Now let's go in here and type, hit an equal sign and type in a couple letters and see what happens. That's how you learn, by the way. Me telling you what it is, you don't learn a damn thing. Excuse me, a darn thing. You really don't, you know, because I'm just talking and you could be thinking about what I'm going to have for dinner tomorrow. I don't know what you're thinking about. But if you do it yourself and play around with it, that's how I learn. I hear a lecture and it's just like, I'm very foggy after a lecture. Then I sit down and do it myself, and that's how I learn it. And most students don't do that. They don't do that at all. They just listen to the lecture, and then when it's time for a test, they read through their notes, and they still don't understand their notes. And then it's a wonderful experience after that. All right. But play around with Excel. Do what I do. Because I don't have these memorized, to be honest with you. When I do this, I just type in the first 2 letters of normal, and then I look down my list and I say, oh yeah, that's the one I need. I don't have it memorized.
Okay.
I don't use it every day. I don't really remember any of this. But that's how I do it. That's how I learn is, oh, I know. I can just type in a letter like T distribution. I just type in my T. And then I say, oh yeah, it's T-D-I-S-T. That's the one to use. And then when I want to do the inverse, I look down the list and I say, oh yeah, T.INV, that's my inverse, where I have the probability and then I need to find the critical value, right? Do that in confidence intervals. But I think I need to give you guys some homework because maybe it'll help you. All right. Any other questions, Han?
No, I'm good.
All right. Now, I realized, because we've been having so much fun in this course, that the semester is almost over.
Yeah.
So here's what I've decided to do. All right. And I don't think you're going to be unpleased. I think you'll be pleased by what I will tell you. All right. All of you are doing fine. You're doing well. And to me, there's nothing in the curriculum that says that we need a final exam. And we're running out of time. So I've decided that we won't have a final exam. We'll just have test number 3. Test number 3 will cover inference. Basically what I cover through next Thursday. This session, this Thursday, and then the two sessions next week. That's it. Whatever I cover, and it'll be confidence intervals, hypothesis test, and whatever I cover from this point forward will be on test 3. Also, I will make sure, especially next week, because you'll be taking test 3, obviously, the week after, which is getting close to Christmas time. So I would probably like you to have that test 3 done by maybe Tuesday, which I think is the 22nd, right? Tuesday the 22nd. Would that work for you
Yes.
guys? Yeah. So, and that way I can get your grades in before Christmas. All right. I believe I have like until the 30th to get the grades in, but I can get them in pretty quickly. Now, in addition, obviously I have to give you maybe a couple more quizzes and some homework. So I will organize all that for you so it's spaced out so you can get it all done. All right. Probably the homework first and then the quizzes. All right. So how's the grading going to work? Well, each test, there's 3 tests. Each test will be worth 20% of your grade. That'll add up to 60%. The quizzes will be 20% of your grade, and the homework projects will be 20% of your grade. And adds up to 100%. Does that make sense? So each little piece, each test is 20%. All the quizzes together will be 20%. All the homework together, 20%. Makes it 100%. All right. And I think your grades will be not much different than what you're seeing now, probably. Once I adjust that, it should be about the same. Should be hardly any different. But that way, there's not that final exam, which would be cumulative, and I don't think you want that. Or maybe you do.
Thanks.
Yeah, sure. So it'll make it easier for you. And as far as covering the material, it won't change what I cover. And actually gives me a little more time to go through things without having to rush, which I think Hans' question today made me realize maybe I was rushing too much, and that's not a good thing. So, so anyway, any questions about chapter 10? There's, again, we have the 3 types of hypothesis tests for one variable, right? We have one population mean where the standard deviation is known, one population mean where the standard deviation is unknown, and then we have population proportion, right? And each one of those has its own formula for the test statistic. But the principle is exactly the same as far as comparing a p-value, right, to your alpha. It's the same principle. Okay, and then of course you have your 3 types of hypothesis tests: the left tail, the right tail, and the 2-tail. Right. So you have theoretically 9 different types of hypothesis tests, right? The 3 types that I talked about in terms of the mean with sigma, mean without sigma, and the proportion. You have 3 of those, and then each one of those could have 3 possible tails, right? Left tail, right tail, 2 tails. So there's 9 possible hypothesis tests you could get, right? From chapter 10, 9 different ones. All right. Now, what about chapter 11? I was going to show you a little bit about chapter 11 today, and that's it. I'm not going to spend more than today on chapter 11. All right. So I think I will open up the book. Let me do that now. Just give me a second here. And I'll open up Cengage textbook. I want you to become a little bit familiar with chapter 11, just so that you understand the difference between chapter 10 and chapter 11. It's not really a major big deal. We still have our 3 types of tests: the Z, the T, and then for the proportion of Z again. There's 3 types again with that. But there is a problem in chapter 11 that we did not consider in chapter 10. because chapter 11 is where we're going to be comparing two quantitative variables. They're actually the same let me rephrase it, the same quantitative variables with reference to two different groups of people, two different populations. So let me get chapter 11 opened up here. Oops, giving me an error. That's not good. What the heck? Try to open up the textbook and it's giving me an error. There we go. All right. You both have your textbooks with you.
Mm-hmm.
Good. So I'm on page six, starting on page. There's a big chart on page 367, which is what I'm going to show you now. All right. Unfortunately, Cengage doesn't give you anything that can make this bigger. Here, I don't think there is. But you have your book so you can see it. And Rose, if you're watching, make sure your book is with you also. This chart actually summarizes pretty much what chapter 11 is all about. What we're doing basically is we're comparing two groups of people for their means or their proportions. Now, when we consider two groups of people, all right, we're saying people, it could be things, so it doesn't have to be people. Typically, the null and alternative hypotheses is in terms of subtracting their means or subtracting their proportions. That's basically what we'll be doing. So we call maybe one of the groups group 1 and the other group group 2. So the null hypothesis typically would be something like mu1 minus mu2 is equal to 0. In other words, there's no difference between the two groups in terms of their mean, the mean of whatever we're measuring. Or if it's a proportions, P1 minus P2 is equal to 0 is the null hypothesis. There's no difference in their proportions. Okay, so it's just a slightly more complicated than what we had in chapter 10. It's not a great big deal. The interpretation is slightly different because we're looking at the difference between means or proportions instead of just looking at the mean and proportion. Where the complication comes in a little bit is in terms of what standard error do we use? All right, because now we have two groups. We don't just have one group, we have two groups. And the two groups could have different standard errors. It's possible. Or we may assume that they have the same standard error. Now, the way this works is there's two methods, two basic methods. Now, before I say the methods, what we're looking at in this box makes one big assumption, that the two groups are independent of one another. In other words, whatever results that we get in one group, it's not affected by the other group. They're independent of one another. So that's one of the assumptions we're making here. Now, later on in this chapter, there is an assumption of dependence. I'll give you an example of that. All right. Again, I'm just giving you a brief introduction to chapter 11. Maybe we'll do a couple problems. We're not going to spend, again, a lot of time on this because this is not as important, I think, to spend hours and hours on this. I just don't. This is just an introductory course. Now, how do we determine what standard error to use? Well, if you look at this chart, it says the hypothesis test is in terms of a mean in this case, it's mu1 minus mu2. All right. 1 minus mu2. Now, this chart, by the way, deals strictly with what? Deals strictly with means. I think there's a separate chart for proportions. There we go. On page 391, we'll get to something like this, all right? But I think for the time being, we'll deal strictly with the difference between two means for two groups. And notice this is like a flow chart here. And so from the very top on the left-hand side, upper left-hand side of the flow chart, it says hypothesis test, and the arrow goes down and says, are the population standard deviations equal? All right, so there's an assumption that needs to be made when you do this test. Now, how do you come up with this assumption? Well, there has to be some familiarity with the data that you have to make this assumption. You may want to, if you were an advanced data analyst, you would probably look at the variability of the data for the two groups and decide by looking at some charts and make a decision if you think it's approximately equal, the variability. If you say yes, then what you're going to calculate just below there on the first column is what's called a pooled estimate of the variance. So you're going to calculate the variance first and then take the square root at the end to get the standard deviation, all right? So in statistics, you didn't learn this because you're not taking what's called a mathematical statistics course, which deals with all the math behind statistics. But in general, the only way that you can add variances together, add variability together, is add variances. You cannot add standard deviations. There's a reason for it, which I won't go into. So you have to add their variances first. Now, if you do a pooled approach, where you're assuming the variances are equal to each other, then the pooled variance, which is this figure here, if you look in the numerator, you'll notice it says n1 minus 1 minus 1. It's the degrees of freedom for group 1. What's n2 minus 1? The degrees of freedom for group 2. What you're doing is you're taking your sample variance, which means if you only have the standard deviation, sample standard deviation, you have to square it to get the sample variance. So you need the sample variance for group 1, the sample variance for group 2, and then you multiply their respective degrees of freedom, add them up, and that's your numerator. The denominator is the sum of those degrees of freedom. N1 minus 1 plus N2 minus 1 is N1 plus N2 minus 2. All right, that's the sum of the degrees of freedom. And then once you have that, okay, you don't need to take the square root of it, because if you look at the formula for the t statistic, which is just below there, what you're doing in the first part of the numerator in the t statistic is you're taking the difference between the sample means of group 1 and group 2, and putting the hypothesized difference, mu1 minus mu2, the null hypothesis, mu1 minus mu2, is subtracted. But in most cases, the difference between mu1 and mu2 is 0. All right, that's your null hypothesis typically, that mu1 minus mu2 is 0. And therefore, typically that second term in the numerator for the t statistic is 0. You're subtracting 0. The denominator is the square root of the pooled variance times 1 divided divided by n1 plus 1 divided by n2, all within that square root. You calculate your t-statistic. That's your t-statistic. And notice your degrees of freedom. It's n1 plus n2 minus 2. Okay? It's not just n minus 1. It's n1 plus n2 minus 2 is your degrees of freedom. And you just do what we did in Excel a little while ago. We calculate our p-value based on that. Everything else is the same. P-value is done exactly like Han and Steve, that's exactly what we just did a couple minutes ago in problem 10.95. Exactly the same thing. All right. Once we have our t-statistic, we just have to realize that when we put in our degrees of freedom, when we calculate t-distribution, you calculate it based on n1 plus n2 minus 2, and just n minus 1. All right. All right. That's it. It's just a bit, the math is a little hairy, but that's it. Now, what if we decide by looking at the data that the variances are unequal to each other? Then we do the middle column here, middle column, which assumes unequal variance. And then it looks kind of complicated. All right, it looks kind of complicated. Actually, the t-statistic doesn't look so bad, does it? The t-statistic doesn't look so bad. Notice the denominator of the t-statistic in the middle column, not so bad. But what you're doing in this case here is you're not pooling the variances now, you're keeping them separate. All right, so in the denominator of the t-statistic, we have the square root of the sum of s1 squared divided by n1. So that's a sample variance of group 1 divided by its sample size, and then plus s2 squared, the variance of group 2, divided by n2, the sample size of group 2. You add those two fractions up, take the square root of it, that's your denominator. The complication comes with the degrees of freedom. That looks like a mess, right? A little bit messy. But that's your degrees of freedom that you would put into your t-distribution when you figure out your p-value. It's a little more complicated, the degrees of. And by the way, it may come out to a decimal. All right, degrees of freedom right now, we've only seen whole numbers, right? But this formula for the degrees of freedom frequently has a decimal, and you include the decimal in degrees of freedom. All right, you include you just type it all in. The computer will handle it. All right. Now, in both the first column and the second column, we make the assumptions that both samples, both populations are normal. Both populations are normal. All right. And the same thing in the middle column. Both populations are normal. We're making that assumption. Even though we're using the t-statistic, which is a different distribution, we're still assuming normal population, all right? Column 3, now, notice that column 2 says for any sample sizes. So for any sample sizes, column 2, all right? Because we're assuming normal distribution for both populations, all right? So it doesn't matter how big the individual sample sizes are. Column 3, it does. Column 3, we're making the assumption, we have to use the central limit theorem. We have to make sure n1 and n2 are both at least 30. The individual samples are both at least 30 for column 3. And the z-test for column 3. which makes it easier, right? Because we don't have any degrees of freedom we have to worry about. All right. So your book is recommending that if your sample sizes are at least 30, right? Go ahead and use the, we're going to call it a Z statistic. Even though the standard error is using sample standard deviations for each population, we're going to actually use the Z statistic here because the individual populations or the individual sample sizes are sufficiently large. All right. They're saying, go ahead and use the Z statistic in that case there. And then we don't have to worry about degrees of freedom. We calculate it the way it's the formula it's given here. And we just use normal distribution for that. Okay. Does that make sense? Sort of. Okay. So those are the three cases for difference in means. One of those three cases. Obviously, if I gave you a problem for one of these, I would give you enough information, you'll know which one of these three cases are used. Now, the question is, does Minitab have some functionality for this? So let's take a look at Minitab. And Minitab do this. And I'm hoping that Minitab can do it for Mac also. If it doesn't, then we're going to have to do it another way. All right, so let's share Minitab. All right, so where do we find this stuff? Well, let's look at under Stat. That might be a good place to look. And I'd say maybe basic statistics would be good. And notice you go down your list, you see two sample T. So it doesn't do it two samples Z, does it? But it does a two sample T. Let's see what it looks like. Okay. So this box, now when you click that in Minitab, do you get a box that looks like this?
Yes.
All right.
Yeah, it's all the same stuff.
If I hit the dialog box down, if I don't give you data, which I won't do in this case, I would probably give you summarized data. Summarized data means you would put in the mean and all the data in the summary information. But notice it gives you this. If you click that, you should get something that looks like this. Do you see it?
Mm-hmm.
All right.
Yes.
So you can put in your individual sample sizes for each of the two groups. So let's do an example. We can do this with. Let's turn to page 373. And problem 11.3. Right there, 11.3. All right. So it's pretty obvious in my review of all this that I'm going to keep with very simple problems. I'm not going to, we're not going to get into complicated. So 11.3, let's read it. Using independent random samples, the researchers comparing the number of hours of television viewed last week for high school seniors versus sophomores. So those are your two groups. All right. The results are shown here. So seniors are going to be grouped. If you look on the next page, it shows you the information that we can just put right into Minitab. Assuming, now the results are shown here, assuming normal populations with equal standard deviations. Equal standard deviations, what does that mean? We're going to use the pooled, right? The pooled variances, right? We're going to pool the variances. Does it appear that the average number of television hours per week could be equal for these two populations? All right. So the null hypothesis says mu1 minus mu2 is 0. The alternative hypothesis would be what? Mu1 minus mu2 is not equal to 0. It doesn't say anything about less than or greater than, so it's going to be a two-tailed test. All right. What is the most accurate statement that can be made about the p-value for the test? All right, let's put in the data. I'm going to type it in. So this for group 1, which is the seniors, the sample size for both of them. What is it? What does it say it is? 32 seniors. So I'm going to put 32.
Yeah.
And 30 sophomores, right? 30 sophomores. The sample means we're going to put in next 3.9 for seniors. And for sophomores, we're going to put in 3.5. For their standard deviations, notice it's not asking for the variance because it's going to do the calculations for us. Group 1 standard deviation is 1.2. And for group 2, 1.4. Okay. Now, obviously, this is not enough information here, right? We have to tell the Minitab that we want equal variances. So we have to hit the options button here. Now, confidence level. Well, what is that? Why are they asking for a confidence level? Well, that's the middle area, right? The middle area. So the question, what are we going to put in there? Well, let's say we do a 5% level of significance. We're doing a two-tail test. That means we're going to have what? 95% in the middle. Is that right?
Mm-hmm.
Right. So this 95% in the middle is equivalent to saying a 5% levels of significance. Does that make sense?
Yes.
All right. Hypothesized difference, we're going to keep it at 0. We're going to say mu1 minus mu2 is 0. That's what they're asking for here, the difference for the null hypothesis. All right. 0. And for the alternative, we have the 3 choices. We're going to say not equal to in this case here. All right. Not equal to. Okay. We're going to assume equal variances. That's what they said, equal standard deviations in the problem. Therefore, we're going to click this box, and Minitab's going to do all the work for us. It's going to calculate the proper degrees of freedom, the proper t-statistics, all of that. I'm going to click that box, hit OK, and then hit OK. And there we go. Wondering what was taking so long. All right, everything we need is right here. Let's take a look at everything that we need, any question we ask. Notice the bottom is our null and alternative hypotheses, right? There they are. That's our two-tail null and alternative hypothesis. Notice it gives us our pooled standard deviation. Nice. Our pooled standard deviation. It actually does oh, I see why it asks for the confidence interval, because it will give us the middle piece as a confidence interval. Okay. All right. Now, the sample difference, the difference in the sample means is given here. That's 3.9 minus 3.5.4. That's where they get that from. And this is the pooled standard deviation. All right. Now, does it give us anything else here that we could use? Does it give us any sort of result? Do we see anything here as a result?
P-value.
Oh, if you scroll down a little bit, there we go. Here is our t-statistic. And here's our degrees of freedom. Now, how do we know the degrees of freedom are correct? Remember, it's N1 plus N2 minus 2. So that's 62 minus 2, 60. This t-value is that formula in the first part. If you go back to that page, right, that formula we saw in that chart, that t-statistic formula in the first column for pooled That's the 1.21. That's our t statistic. So if I ask for that in a multiple choice question, right? I can ask what's the degrees of freedom. I can ask what the t statistic is. I can ask you what the p-value is. Now this p-value, by the way, is the sum of the left tail and right tail areas. It's already calculated it for you, all right? That's the full p-value. Each tail would be something like 0.1155 or something like that, whatever it might be. And you double it and you get this 0.231. Do not double this number. This is the correct p-value. It's giving you the correct p-value. That's why I don't teach this to regular students, because they're going to think, oh, I have to multiply by 2. And they get all confused. All right. The computer has already done all those steps that I've mentioned to you. It's given you the answer here. Now, one thing I want to bring to your attention is it does not give you the result of the test. Do we reject or not reject the null hypothesis? But I want to show you something that's really good about this just for a two-tailed test. Notice that the confidence interval, which would correspond to a two-tailed test, by the way, the confidence interval here does contain 0, the null 0, doesn't it?
Mm-hmm.
All right. And that means do not reject. Also, the p-value is 0.231. In most cases, no matter what we pick for alpha, typically we pick alpha to be 0.1 or less. This is bigger than alpha for all those cases. So in this, we're going to end up not rejecting the null hypothesis. So the conclusion is, if we use, let's say we use 5% at the as a significance level, we would say something at the 5% significance level, there is no difference. There's no evidence that there's any difference between seniors and sophomores in terms of number of hours that they watch television. Number of hours they watch television last week. Doesn't seem to be any difference. There's not enough evidence to show that there's any difference. All right, let's put it that way. There's no evidence to show that there's any difference in television viewing. All right. Does that make sense?
Yes.
Because the alternative hypothesis is that there is a difference between them. It doesn't say which group watches more television. It's just say that there's a difference, and there's not enough evidence to show a difference here. It's not that bad, right? It's not bad at all. It's just that, the formulas are time consuming, so it's okay to use Minitab in this case. All right, because Minitab's going to give you. Now, Minitab, I believe, if you go back to stat and look at basic statistics again, it gives you a 2-sample T, but it does not give you a 2-sample Z for means. It gives you a 2-sample two proportions, but it doesn't give you 2-sample means. So here's the deal. We're going to make the assumption. That we're going to use either the pooled t-test or the unequal variance t-test, and that's all we'll say. All right, we're not going to do that third column at all because Minitab doesn't have that here. All right, this book here is old. That third column, maybe people don't use anymore. They don't do that anymore. They just use one of the t-tests. All right, and that's it. They use one of the t-tests. So that's what we'll do here also. And let's assume, because, to be honest with you here, they calculated a t-value here, didn't they?
Mm-hmm.
And in both cases, notice that there's more than 30 for the sample sizes for each one of these groups here. So They could have used that third column, but they didn't. And I think in real life, you don't use a two-sample z-test for means. You typically do a two-sample t-test. All right, that's the typical one. So let's just assume that. That's what we'll do that from now on and not do a two-sample z-test for means. Now, for the proportions, it's different because we will do a two-sample z-test. So let's see if we can find an example of that. Two-sample z-test. And that would be, let me tell you what page to go to. That starts on page 391. Let's go actually stop sharing here. And let's go to our textbook. And let's go to page 391. Let's just go here. So annoying. They are so annoying. How can it be expire already? We haven't even been on this very long. So annoying. All right. Let's see. All right. So it's here it is. Section 6, chapter 11. All right. So how do we do it? Well, there is a chart for this too, and it's on page 91, and it looks really, it does look complicated. Here's your Z statistic. The numerator is, now we're assuming that the difference in proportions is 0 in the alternative hypothesis, all right? We're making that assumption. That's why the numerator simply, and by the way, when you look at this here, the P represents what? It represents the sample statistic, but we're using P hat, right? We're using P hat. So think about, these are sample statistics. So P hat 1 minus P hat 2 is our sample, the difference in sample means. We're assuming the difference in population means is 0. That's why they don't have anything after that. And your denominator is a strange formula here. So we have to go through it. It has a P bar above it. You see these P bars? It tells you what P bar is below it. This is pretty complicated, right? You calculate this P bar first, and the P's represent what? They represent the sample statistic. So it gets kind of hairy with all of this. Once you calculate P bar, then you put it into the Z statistic formula. It's, you know, it's hairy. So anyway, and then that assumes what? We're pooling the variance. We're pooling the variance. And then we have the unequal case. Oh, I see. All right, let me just restate it. If this first formula assumes that the hypothesized difference in proportions is 0, and then if you look at the second case, it's assuming that the hypothesized difference is something other than 0. In other words, it's equal to 3 or 0.3 or something like that. And then we have these really complicated looking formulas. So what's the solution? We're going to use Minitab, all right? So we're going to actually pick a problem in this section. All right. Let's look at problem 11.53 on page 395. Okay. And then we're going to pick the two proportion test. Again, it's under basic statistics, go down to two proportions. Once again, I'm going to choose summarize data. It's going to look a lot like what we did before. Okay. And if you look at 1153, just enter the data in there. Just put it right in there. Now you have to remember that the P's mentioned in the problem there are sample proportions. All right, so if I gave it to you on the test, I would put P hat instead of P, all right? But there's sample proportions. So you just put in the proportions, and it says number of trials, that's just the sample size. So for sample 1, all right, for sample 1, we're going to put in 0.31. Actually, it says number of events. Number of events, number of trials. Oh. Any ideas? What do I put in for number of events? It's not asking for a proportion, is it? Look at 11.53. It's giving you a proportion and the sample size. The sample size is the number of trials. So we could put those in, 400 for group 1 and 500 for group 2. But what am I going to put in for number of events? What do you think? Well, for the first group 1, I'm going to put 124 in there. And for the second group, I'm going to put 145 in there. How did I come up with those two numbers? Where did I get those from?
Oh, you multiplied 0.31 by 400. And
Well, I made a mistake in the second one, didn't I? I was looking at the wrong.
0.38 by 500.
Yeah. Well, I was right. Was I right about that? 0.38 times 500? 38 times 500. Yeah, I was wrong about that. It should be 190. This should be 190. First one's right, I believe, right? 124?
Yes.
Yeah. That's where I got them. So you have to actually enter in the number of successes. Normally we call them number of successes, but Minitab calls them the number of events. All right.
Would you mind sharing your screen for Minitab? I'm a little bit lost with navigating through Minitab.
Oh, I don't have it shared?
And we're looking at the book right now.
All right. So let's share it. Where are you? Let me cancel it out. You just go to Stat, Basic Statistics, and go down to 2 proportions. And then your dialog box picks Summarize Data. You have that?
Yep.
Just enter it in here, what we
Okay.
just said. Yeah. So number of trials would be the sample size for both of them. One, it would be 400 and 500. Number of trials. And then for the number of events, it would be the proportion. If they don't give you the count, then you have to calculate it. So the first one was 0.31 times 400, which is 124. And then the second sample, 0.38 times 500, which is 190. All right. Now options, we have to go to options because we have to determine. Now we'll keep it. The confidence level I'm not worrying about because that gives us a confidence interval, right? And I mean, it's not going to be very helpful, by the way, if we want to do a one-tail test. In this case here, it's a two-tail test, so there's no problem with that. The hypothesized difference is 0. And we want the alternative to be not 0, right? Because it gives us the 3 cases here. We're going to pick not 0. The test method, it says there's two cases, right? We estimate the proportion separately or use the pooled estimate. Now, it doesn't tell us here. Does it tell us what to do? It doesn't say which method to use in 53, does it?
No.
Okay. So I might have to tell you which one to use. Let me just see something for a second. Oh, wait a minute. It depends on whether the difference is 0 or not, right? If you look on page 391 in your text, it says if the hypothesized difference is 0, the usual case, we use the pooled method. All right, so that's what we're going to use. We're going to use the pooled method. Make sure you do that. It says use the other method if the hypothesized difference is not 0. All right, so it doesn't default to this, you have to choose it. Use the pooled estimate. All right. All right. And that's it. So click OK and click OK again. And scroll down a little bit. Actually gives you 2 p-values. Just use the normal approximation if there's any difference between these two. All right.
Mm-hmm.
They're the same. 0.029. And then once again, if I gave you an alpha, you would compare it to alpha. So for example, if I said alpha is 1%, you would say do not reject. If I said alpha is 5%, you reject. Remember, this is the full p-value. It's already doubled the individual tails. All right, it's already doubled it. So don't double it again. All right. Any questions about that?
Did we have a alpha for 53? The question 53?
No. Well, it might have given you. Let me see. Yeah, 5%. It gives it in the problem. Right? It says it right there. It's a 0.05
So there's
level.
significance.
So you would reject.
Oh, okay, okay.
Yeah, it should be always given to you. Right?
Mhm.
All right. Let me see if there's anything other than worthwhile looking at. Here's one. If you look at 55 on that same page, number 55, they're comparing 2 groups. They give you 2 proportions. You read through it, and then they want to know if one of the groups has a greater or just greater in proportion. So in this case, the difference in proportions would be 0, and the well, it depends on what you set up as P1 and P2. Now you have to be careful here. Be very careful. Whatever you set up as sample 1, make sure you know which of these 2 groups you're talking about. Right? When you do a one-tailed test, you got to make sure that you know which is group 1 and which is group 2 when
Right.
you enter it. You have a choice, don't you? Correct?
Mhm.
Yeah. So make sure that you set this up correctly so that you read the results correctly. Right? If you have it backwards, then the test would be less than, not greater than. So make sure that you would have, for example, group 1 would be the conventional case, and group 2 would be the touchscreen case. All right? That's the way you would want to set up. So therefore, you would put your 0.8 as group 1 and 0.75 as group 2. The question, of course, is what would you actually enter? Well, it says each. So you'd have to put 500 as your number of trials for both of them. And then you would do 80% of that, which is 400, for the numbers of successes for group 1, and 75% of 500, which is 400 of, or not 400, 3/4, 300, right? 300, whatever the number is. 3/4, whatever that number is, 3/4 of 500 you put in for group 2. Did you want me to show you run that? Shall we run it really quickly? Because you can run these really fast, right? This is really fast. You do it this way. So 2 proportions again. You click the last choice. We're assuming that they're equal to each other. There's nothing in here that says the null should be something other than equal to each other, right? Assume the percentages to be based on independent samples. All right, 1% level of significance. So unless they say otherwise, you're going to assume the null hypothesis is that they're equal to each other, 2 proportions. All right, so we're going to put 500 in for group 1. And then group 1 has 80% of that. That's 400, right? That's 400. And group 2 is 75%. 500. What? What is that?
375.
375. That's right. 375. Then the options down here. Again, confidence level doesn't matter. Hypothesized difference is going to be 0. Alternative hypothesis not equal. We have to change this, right? We're going to say greater than in this case here. Difference is greater than the hypothesized difference. Make sure you choose that. That's a right tail test. We're going to use the pooled estimate. Hit OK. Hit OK again. And there's our results. And please use the normal approximation p-value. All right. It says it gives you the Fisher's exact. I don't know what that means. Just use the normal approximation 0.029. All right.
Mm-hmm.
I might even state it in the problem. Use normal approximation. I asked for the Z statistic. This is it right here, 1.89. That's our Z statistic. Okay. And if the alpha is 0.01, in both of these, it doesn't matter which one you choose here, but we're going to use 0.029. It's bigger than 0.01, so we do not reject the null. If it's 5%, we would have rejected the null. All right. Now, the question, of course, would be, and by the way, section 7, I'm skipping. That's an advanced topic. It basically is a test to see which of the unequal or equal variances do we choose. There's an actual test for it. We're not going to do that. It requires us to learn some other distributions called the F distribution, which is more of a second semester topic. Now, what if, and here's a big what if the 2 samples are not independent? An example of that would be somebody who, let's say we were checking the results of a blood test or something over time, right? Maybe they got the test at one time period and the same person received the test a second time period. And we want to know if there's any significant difference, you know? Maybe time period 1, they they didn't take any medication. Time period 2, they took some medication. All right, whatever it is. We're checking to see if there's any difference between that person between time period 1 and time period 2. Obviously, the 2 events are dependent on one another because it's the same person, right? You can't say they're independent. It's the same person. So what do? Well, you can't do a one of these tests that we've just done, because these assume independence. So what we have to do is actually make sure that each person is recognized in both time periods. And what we do is we subtract their individual values for each of the time periods, and then take the mean of those differences. What does subtraction do? Subtraction gets rid of the dependence, right? Any dependence, if it's the same person, there might be multiple factors that might be affecting the result of the test, right?
Mm-hmm.
How do you get rid of all those factors? You just subtract the numbers. When you subtract the numbers, you're getting rid of all those other factors, right? You're literally getting rid of them. So this is called a paired t-test. Paired t-test, okay? And let me see if I see an example in here. There is. Page 385. So what do? It's almost like an ordinary one sample t-test, because once we subtract the individual values for each person and then take the mean of those differences, we end up with basically one mean. And that's what they mean by mu d there. The d represents differences, match pairs of observations. Now, it doesn't have to be the same person. It could be pairs of people who are dependent on one another. There's some dependence there, all right? So it's an advanced topic, but ultimately it looks quite like what we chapter 10 problem. All right, and typically you have data. And you enter the data and then let the program do it for you. For example, in here, you see a pair T as a are we looking at we're looking at Minitab, right? You're looking at Minitab right now? Are you looking at Minitab right now?
Yes.
Yes.
All right. So you just choose pair T. Now you could actually put in summarized data here if you had it. Sample size, the sample mean. What's the mean in this case here? Would be the mean of the differences between the two groups. All right. Typically, you give people data and they figure it out, right? They put in the two data sets but if you were given the difference, the mean of the differences, that's what you would put in here. You put your sample size here. You put the standard deviation of the differences here. The option, well, there's not much of an option here. You just put that, you assume that there's no difference at all as the hypothesis, as the null hypothesis. And then the three cases would be either there's an increase in the value, a decrease, or there's no difference, or there is just a difference, significant difference. All right, and this looks very much like a regular one sample t-test. All right, and you don't see this with proportions, just with means, because, right, why would you do it with proportions? Doesn't make any sense, right? Usually with means. This is called a pair T, and typically you'll enter the data, have the data entered for both groups. What's required, of course, is that n has to be the same. The sample size has to be the same for both groups if you're going to subtract values, right? It can't have unequal sample sizes. That's pretty easy to do. All right, that's it. That's chapter 11. Without getting into all the, the hairy complications, I've pretty much told you chapter 11. So what are the three cases again? Two sample t-test for means. all right, we do a t-test and then we choose whether we pool or not, or we don't pool the variances. Okay, those are, and then we have the case of what? The proportions. And that's it. And then we have the, and that's for independent samples. Then we have the dependent sample case. We simply subtract each value from the 2 time periods, right? We subtract the values and then do a t-test on the difference. All right, that's it. It's pretty much the same idea as chapter 10 in terms of coming to your conclusions. You calculate a test statistic, you calculate a p-value based on it in the same exact way, except we have to make sure we use the correct degrees of freedom, right? When we do the pooled t-test, right? Pooled t-test, make sure you use, and when we do a z for difference in proportions, there's no, the degrees of freedom are what? There's no degrees of freedom for proportions, right? It's a z-test. For the pair test, it's just, it looks strictly like a pair t-test. It looks strictly like a regular t-test. All right. Just a normal t-test. And it doesn't even look like it's asking for degrees of freedom at all here. It actually knows how to calculate it. You don't even have to worry about degrees of freedom. Actually, if you look at page 387, gives you, some information about the calculations, and it uses n-1 degrees of freedom. So it looks like a standard regular t-test.
Mm-hmm.
Yeah. All right. So that's it. That's chapter 11. And again, I'm going to start assigning homework. I think the last homework we did was chapter 9. Did we do confidence interval homework? We didn't do confidence interval homework, right? So I have to give you homework for chapter 9, for chapter 10, and for chapter 11. All right. Not much from chapter 11, just a, maybe 3 problems from chapter 11, just examples of the types of things I could ask on a test. All right. And what are we going to do next time? Let me stop sharing for a minute and let me find, if I can, I don't want to show you that. let me find the syllabus for this course. I want to double check it again. So let me find it. All right, so let's see if I can find the syllabus for it. There's the syllabus. Tentative schedule. Let's look at the tentative schedule. Actually, give me a second here. This is the syllabus from the department. Let me see what they have here. According to the syllabus, hypothesis tests involving 2 sample means is all that they have in here. However, it's very easy to do the difference in proportions too. So there's no reason why I can't show you that one. It does not have the pair T in here. So I just showed it to you, but you won't be tested on that. So I should give you examples of both the independent difference in means and also independent difference in proportions, because it's very easy to do it in Minitab. Both of you can do that. The only thing that's left is regression, all right, in the syllabus. So we're going to actually jump to chapter. No, 15. We're going to skip 14 also. And starting on Thursday, we're going to start chapter 15. And we may go back. Let me get back to seeing you again. Here we go. We may go back to an earlier chapter when they showed scatter plots. So I'm going to show you how to do scatter plots in Minitab, and then we're going to do a couple different regression models. Chapter 15 regression. We're going to spend 3 meetings on regression. So we'll start tomorrow, and we'll go into next week. And because regression is an important topic. Chapter 15, we'll definitely do. And we will not do chapter 16, which is multiple regression, which is obviously the more common one. Simple regression is very rarely used because typically you have more than 2 variables that you're comparing. You may have hundreds of variables that you're looking at. So we'll talk about the assumptions of linear regression next time, and then I'll show you some ways of doing it. And I might even, as a treat, if you want to consider it a treat, I might even show you how to do bivariate regression, which means we'll have a dependent variable and 2 independent variables. Because I think we can do that. Let me just take a quick look. I think we can do that in Minitab. Let me just double check regression. And no, I think I might not want to do that. Let me just check one other thing here. What I'm thinking about. No. All right. Oh, here it is. 2 quantitative predictive variables. All right. So that's in chapter 16. It depends. It depends how you're doing. If it doesn't look like it makes any sense, we'll stop in chapter 15 and just call it a day. All right. Because typically in an introductory class, we don't go past something like chapter 15. But since now, Steve, did you say you're going to take an additional course, maybe?
Not next semester, but possibly.
Sometime, right? And Han, are you planning to take anything more than this course in statistics?
I don't know yet.
You don't know yet? Okay. All right. All right. Let me think about it, but let's spend 3 sessions on regression. All right. And it'll be worth your time. You'll learn a lot from this chapter. And we'll work with Minitab, because Minitab will give us all the reports that we need to answer questions regarding regression. Okay, so that's it for tonight. I'm going to stop the recording, and